Hey guys, welcome. Yeah, so here we're gonna define logs, talk about logs in detail, and one thing I frequently encounter is that a lot of students dislike logs or they don't understand them, but they're like one of my favorite things. They're really cool and they're fun, and so hopefully by the end of this video, I've convinced you of that. Okay, cool. But let's start here. So first, we would write log and then some base a of x equals y. So this here is a function, and it's a function that depends on x. So the input is x, and of course there's this base a, and we need to fix a. That is, specify what a is. But a is not the input, x is. In other words, x is the argument. Okay, cool. So what we're saying is log base 2 of x is a different function from log base 3 of x. Yeah? Okay. So if this is called f of x, log base 2 of x, then we must call this something else. Let's say g of x. Yeah? Okay, cool. But let's move forward from here and define what we mean by it. What do we mean by log base a of x is equal to y? How do we define that? Well, that's the definition of logarithms. The definition is that this is true if and only if a to the y is equal to x. And this here is the same thing as that, because if and only if is two directional, right? So if and only if means that if this is true, then this has to be true, but also that if this is true, this has to be true. And this is called the exponential form, and this is called the logarithmic form. So this logarithmic form always implies this exponential form. So what I'm saying is an interpretation of this is that. So let's fix a. In other words, let's decide what a is. So say we're talking about the function log base 2 of x and evaluate it at a few values. One is, let's say, log base 2 of 2. What is that? Well, we know an interpretation now. So log base 2 of 2 is equal to y if and only if, this symbol means if and only if, it's the same thing. If and only if 2, which is a, right, to the y, right? So 2 to the y is equal to x, right there. Yeah, if and only if 2 to the y is equal to 2. Well, 2 here can be written as 2 to the first. So that would mean that y is equal to 1. So we see that log base 2 of 2 is equal to 1. Now, I want to show you how to evaluate log base 2 of, like, say, 32 and other things. But let's come back to that in a second. Let's first look at a curious little thing, which is we saw log base 2 of 2 as 1. What if we wrote log base 3 of 3? Well, we'd say that this is equal to y, and we'd say that this is true if and only if 3 to the y is equal to 3. And then we'd immediately see that that means that y is equal to 1 again. Hold on. So, what about log base a of a? What is that equal to? Well, let's say it's equal to y. We know from our interpretation that this would mean that a to the y would have to equal a, which means that y is equal to 1. Cool. So you see, in general, log base a of a is equal to 1. It doesn't matter what the base is. Log base a of a is equal to 1. Okay, cool. That's a nice little thing to know, right? Okay, cool. Now, kind of like similarly motivated to see the patterns, let's look at log base 2 of, we've already seen log base 2 of 2, so I guess it's natural to consider log base 2 of 1, right? In fact, I'm surprised we didn't start there. Okay, so we'd say that this is equal to y, and then we'd say, based on our interpretation, that this would mean 2 to the y is equal to 1. Well, that would mean y is equal to 0. So that means log base 2 of 1 is equal to 0. But let's do what we did earlier. Let's look at log base 3 of 1. Well, this is equal to y, and this is true if and only if 3 to the y is equal to 1. You get it, you get it. Y again has to be 0. So log base 3 of 1 is equal to 0. We saw that this was true. We saw that this was true. Okay, we don't even have to say log base a of 1. You can try it on your own, but it's pretty clear now that log base a, let me rewrite that, that log base a of 1 is equal to 0, regardless of the base a. Okay, cool, cool. A nice other thing to conclude more generally, right? Okay, okay. Now, as per promise, let's look at evaluating like harder logs, like log base 2 of like 5, because both log base 2 of 2 and log base 2 of 1 had some nice conveniences about them. What about this? Well, we'd say it's equal to y, and we would seek to find a y so that 2 to the y is equal to 5. I don't know about you, but my hands are tied. I don't know a number y immediately, which when you raise 2 to the y power would give you a 5. Surely we know that there's a number and there's a way to evaluate it, but we would need a calculator. So to evaluate this, you need a calculator. You cannot know this without a calculator. And that's just like, yeah, there's no human that knows log base 2 of 5, like offhand. Okay? All right, cool, 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 cool. So there's that. But what about log base 2 of 32? Well, 32 has a convenience about it. So we can find out what this is without a calculator, because we can write that we have 2 to the y is equal to 32. But 32 can be written as a power of 2. So we can say 2 to the y is equal to 2 to the 5th. And 2 to the 5th, as we all know, is 32. And so we conclude that y has to be 5. That is, we conclude that log base 2 of 32 is equal to 5. Yeah? Okay, cool, cool, cool. All right, all right. And so similarly, you know, log base 3 of anything that's a power of 3, or it can be written as a power of 3, is something we can evaluate without a calculator. So in fact, let's consider log base 3 of like 1 over 27. Well, what is this? We'd say, and I'm using question mark instead of y, but yeah, sure. We still have an interpretation as long as you've got the equal sign and something written on the right side of the equal sign. This time it's question mark. But based on our interpretation, that means that we would seek 3 to the question mark is equal to 1 over 27, right? Okay, that means we would look to find 3 to the question mark is equal to 1 over 3 to the third. But then we can write 1 over 3 to the third is 3 to the negative 3. So question mark is clearly negative 3. In other words, log base 3 of 1 over 27 is equal to negative 3. Cool, cool, cool. All right. So you see, like, you know, as long as like you could write the argument as a power of 3, then you could evaluate it without a calculator. And the same is true in general. As long as this x here can be written as a power of a, then you can evaluate the log without a calculator. But otherwise, you'd need a calculator. Okay, cool. Let's, I guess, do like one hard one. Well, yeah. Log base like 2 of like, I don't know if this is particularly hard, but log base 2 of, I'm trying to think, sorry. Log base 2 of what? Log base 2 of root 32. That's, I guess this is equally like easy. We'd say that this is y, and 2 to the y is equal to root 32, and that's 2 to the y is equal to, well, we know root 32 can be written as 32 to the 1/2 power, because square root means as an exponent 1/2, and then 2 to the y is equal to 32 is again 2 to the 5th, so we have 2 to the 5th to the 1/2, but that using exponent rules, that is this using exponent rules, can be written as 2 to the 5/2. So we'd say that log base 2 of root 32 is equal to 5 halves. And this isn't particularly hard. I was kind of trying to think of something harder, and I'll like do one other one I think is like maybe slightly harder than this, which is like, what about log base 8 of 4, right? Well, we'd say that this is equal to y, and we'd proceed as usual. We'd use our translation, and again, this is called the exponential form, and this is a logarithmic form. And since this is in logarithmic form, we would want to translate it to the exponential form, which is all we've been doing so far. So we have to write that 8 to the y is equal to 4. And although like it's not clear how to write 4 as a power of 8, and it's not possible, right? We could 8 to no power. Well, we're gonna see, but like we can't write 4 as 8 to an integer power, right? Okay, that's what I'm saying. Anyway, even though we can't do that, right? We could use the fact that both 8 and 4 can be written as powers of 2, so we can compare exponents. So 8 we write as 2 to the third, and then we have 2 to the third to the y is equal to 2 squared. And then that means that we have 2 to the 3y is equal to 2 squared. And so that means 3y is equal to 2, from which we gather that y has to be 2/3. So log base 8 of 4 is equal to 2/3. Yeah? Okay, cool. I hope you're also like kind of seeing relationship between the arguments and the bases and so on as we're looking at evaluating some logs. And yeah. Okay, cool. So what's next? What should we discuss next? Well, next, let's see if a can be a fraction, because so far we've been working with integer a values, right? So in other words, can we have log base 1/2 of like say 4? If we say that this is equal to y, does this make sense? Well, let's see. So we would say that this means, based on our translation, that we have 1/2 to the y power is equal to 4. And 4 can be written as a power of 2, and we could also rewrite this so that it's 2 to some power. First, the 1/2 can be written as 2 to the negative 1, and we have 2 to the negative 1 to the y, and then the 4 can be written as 2 squared. And so we have, from here, right, from here we have 2 to the negative y is equal to 2 to the second, which means that y is equal to negative 2, right? Okay, cool. So we can evaluate this, and therefore like 1/2 or a fraction like that is permissible as a log base. Okay, and we're gonna keep investigating what other values of a are possible. So let's consider log base 1, right? Okay, log base 1. So log base 1 of, let's say, 3. If this equals y, what are we saying? We're saying 1 to the y power is equal to 3. What? There's no power y you can raise 1 to get 3. If you raise 1 to any power, you get 1. So 1 is not permissible as a log base. So a is not allowed to be 1. So we add that to the definition. Cool. All right. And of course, naturally, next we consider, notice I've considered 1/2. So you're allowed to be less than 1. You're just not allowed to be 1, right? And we've obviously looked at 2 and stuff, so we know you're allowed to be more than 1. What about like lower than 0, right? Okay. And naturally, you see log base 0 doesn't make sense either, right? Like 0 to what power is going to equal 3 if you have log base 0 of 3, right? Okay. And so 0 is not permissible. We see that. But like, what about negatives? So what about log base like negative 3 of like 27, right? So here we say that equals y. And so we're looking for negative 3 to the what power is equal to 27. Well, negative 3 to what power is equal to 27 means since 27 can be written as a power of 3, we have 3 to the what power? Well, 3 to the third. We know that's 27. My bad. So we're saying like negative 3 to what power is equal to 3 to the third? No power. There's no way you can raise negative 3 to a power to equal 3 to the third, right? Like that doesn't make sense. So negatives, and I'm only using like one example here, but negatives are not allowed for a base A, right? Okay, so 1 is not allowed, negatives are not allowed, 0 is not allowed, so but fractions like 1/2 are. So we conclude that A must be greater than 0, but also A cannot equal 1, right? So those together allow us to define the characteristics of the base A. But anything else is game. You can do any other log base. Yeah? Okay, cool. And in fact, there are 2 special logs that I'll write in a different color. And those 2 special logs are log base 10 of x. Log base 10 of x is so special and popular that it's frequently written without the base 10 showing. So it's frequently written as just log x. So if you see log x, you must automatically assume that it's written in base 10. Because log x, well, at the start of our discussion, we said all logs come with a base a, right? So if log x is written without a base a, then it must be that the base is 10. And that's just convention. So in every book, this is true. Yeah? Okay, cool. All right. Also, if you know the number e, which is a special number, right? Log base e of x has a special name, and it's ln of x. People like read it in so many different ways. They say ln and all this other crazy stuff. This is L, and this is an N, and it's ln of x. And again, this is not just written without a base, but like, different symbols entirely. But it just means log base e of x, where e is that special number approximately equal to 2.7, right? And again, log base 10 of x is just log x. Yeah? Okay, cool. I'll keep that here. And so the only thing left to do then is to figure out what x can be. Like, is every x possible, or are certain x's not allowed? Well, so we've seen log base 2 of 2, and we said we even know what log base 2 of 5 is. We just need a calculator, because we would know that log base 2 of 5 is something, question mark, means that 2 to the question mark is equal to 5. And so we know that there's a number to replace question mark, so that this is true. We just can't do it without a calculator, because 5 cannot be written as a power of 2. So we know that positive numbers are allowed. And we already evaluated log base, any base of 1, and we stated the result here. So we know even 1 is allowed. And we even evaluated log base 3 of 1 over 27. And we said that was negative 3. So we know that fractions below 1 are allowed. But what about log base 3 of 0, right? So what is log base 3 of 0? Well, we would need that 3 to some power would equal 0. Well, you see there's no exponent of 3 that would get 3 to that power to equal 0. So we see that we cannot evaluate logs where this x is 0. And so the only thing then to talk about is, can we evaluate logs where x is negative? So for example, log base 2 of negative 4. Well, this we'd say equals y, and that have to imply that 2 to the y is equal to negative 4. But wait, there's no y, so that 2 to that power equals negative 4. So we see, although I'm only again using one example, that negatives are not allowed. So here, the domain of logs, which is the permissible x values, are greater than 0. Anything, any x value greater than 0 is permissible, but not anything else. So domain of log x is all x greater than 0. Yeah, okay, cool. Those are the inputs, all x greater than 0. So this is basically like what the definition of logs are. Like, I'm tempted to say more, and because, you know, you could talk, I said I love logs, so we can talk about them like forever. But like, you know, like I could just like make other videos because like, yeah, like I think this is like good enough, and maybe if I say more I'll like confuse you and like, yeah. Okay, instead of yeah, this is helpful enough. Okay, cool. So, you know, it goes without saying that, you know, like I'm gonna make lots more videos about logs, and in fact I've already made a few more, and you know, so that you're on the lookout for them. Like, these are some of the videos to come. One is like logs have like these special rules, and one of them is called the power rule. And so I'll make a video about the power rule, but also a video on proof of the power rule. So the proof is another video, proof of the power rule. And then 2 is quotient rule. So there's a quotient rule for logs. And that, and then also the proof of the quotient rule is another video, quotient rule proof. And then there's a third rule, which is very important also, called the product rule. In fact, I kind of wrote them out of order. The product rule is the most important thing after the definition of logs. And then the other 2, you know, are equally important. So power rule and quotient rule, equally important. Product rule is the most important thing to know about logs after the definition of logs. Okay, product rule. So I'll have a video on the product rule and also proof of the product rule. And I already have these videos out, by the way, so you could already watch them. And other than that, I'll show you how to do what's called expanding logs. So videos on expanding logs, and then I'll show you how to do what's called condensing logs. And so you probably saw this coming after saying expanding logs. But yeah, condensing logs. And when I say logs, I mean, of course, logarithms. And so I'll have videos on both. And I'll have videos on logarithmic equations. And then also on what's called the change of base formula. So you can change from one log base to another log base using the change of base formula. Yeah, and I will prove this change of base formula. It's a short proof, so watch that. So proof of change of base formula is another video. And finally, like you see, there's a lot of logs to come. I'll just do cool problems involving logs, and logs are like a contest math favorite, which is like if you do math competitions, so the AMC exams or any other math contests, they love logs because you can construct like interesting and easy problems, or hard problems that you can solve like through easy and clever methods. So like I'll have a lot of contest problems that I'll solve in the log video. So check all this out, and yeah. Okay, take care.